Say, that must be one of those new one-cylinder disc brakes. I still don't see how it works and how one cylinder can do the work of the 4 cylinders we have in our other disc brakes.
I can see you have a lot to learn about this new brake, Joe. In the first place, it's called a single piston floating caliper disc brake. But maybe Tom and I better explain exactly how it works. How about it, Tom?
Sure thing, Tech. Let's get acquainted with the main working parts first, Joe. Notice that the disc is much thicker than the ones used with our other disc brakes. A positive method of retaining the shoes in the caliper makes it safe to reface the discs. However, if you reface one side, you must reface the other side without rechucking the disc. That's the only sure way of holding the maximum allowable variation in thickness to 1/2 thousandth specified.
1/2 thousandth? Is it really necessary to hold it that close?
It sure is, Joe. More than 1/2 thousandth variation in disc thickness will cause objectionable brake pulsation. There's no reason why you can't hold that spec if you use the right kind of refacing equipment.
How about disc runout?
The maximum allowable runout, measured 1 inch from the edge of the disc, must not exceed 2.5 thousandths.
Well, how much metal can you take off when resurfacing a disc?
You must not remove more than a total of 50 thousandths of an inch. And you must not reduce disc thickness to less than 1.2 inches. For example, this could be 40 thousandths from one side and 10 from the opposite side, or any other combination that doesn't exceed a total of 50 thousandths.
You'll find all of the details of inspecting discs, measuring runout and thickness, and machining discs in the service manual. So let's look at the rest of this brake.
The adapter is the backbone or fixed support for the brake assembly. It's bolted to the steering knuckle, so it takes all of the braking loads, something like the support plate and anchor of a drum brake. Now let's look at the movable caliper. The caliper is a one-piece casting with a single cylinder bore on the inboard side of the brake. A square-cut rubber piston seal fits into the machine groove in the cylinder bore. A large single piston is used. It's nickel and chrome plated to provide very good resistance to wear and corrosion. A rubber dust boot protects the piston and cylinder bore. But let's see how these hydraulic parts look in cross-section. When hydraulic pressure is applied to the piston, it moves outward, and the seal moves in a rolling motion with the piston. When the brakes are released, the distorted seal acts like a return spring and pushes the piston back into its bore.
The way that dust boot works is kind of interesting too, Joe. The dust boot forms an airtight seal at both the piston and cylinder. A lip rides on the piston to keep the boot in its groove inside the cylinder. The other lip of the boot is a tight fit in the piston groove. Now here's some servicing musts. A special tool should be used to remove the piston from its bore. This will reduce the possibility of scratching the piston surface, which is the actual pressure sealing surface. Do not use air to blow the piston out of the bore. It's extremely dangerous. A special hone is available for cleaning up the cylinder bore. Be sure and hone the land between the piston and the seal grooves. And it's extremely important to clean out both these grooves. A bronze wire brush and a little brake fluid will do the trick. Don't scrape any metal from the grooves. Do flush out all traces of dirt and grit after cleaning or honing. Never reuse a seal or dust boot. Install new ones. Use the special lube provided with a seal kit when assembling these parts. Don't use any other type of lubricant. And don't use a hard or sharp tool to install a seal or the boot. Use your fingers. Maybe you better show Joe how to install that boot.
Glad to, Tech. Lubricate the boot with a special lube provided, and using the fingers only, work the outer lip of the boot into the groove in the cylinder. Then close the bleeder screw and plug the pressure inlet with a brass plug having the correct thread. Next, lubricate the piston. Slip it through the dust boot and line the piston up squarely with the bore. Press down on the piston, and the trapped air escaping past the piston seal will pop the inner lip of the boot into the boot groove in the piston, slick as a whistle.
You'll find complete service instructions in your service manual. However, some of the tips and precautions are worth repeating. We'll flag them as we come to them. Now, let's get back to our caliper.
The brake shoes fit into the caliper. The inboard shoe rests against the piston. The outboard shoe simply bottoms against a machined surface at the outboard end of the caliper. And now let's take another look at the adapter. 2 steel guide pins are threaded into the adapter. That means they are stationary or non-moving parts. They help guide and position the caliper as it floats in and out. When assembling the brake, the 2 guide pins slide through 4 rubber bushings in the caliper. The guide pins also pass through holes in the brake shoes. This provides positive shoe retention in the caliper. Now let's take a look at the assembled adapter and caliper. When the guide pins are installed, positioners at the inboard ends of the pins hold the caliper outward when the brakes are released so that the outboard shoe is away from the disc. They actually bend and close up as the linings wear. Because of this, you must use new positioners when new shoes are installed or the caliper is serviced. You must also install new rubber bushings because caliper movement gradually wears them. Here's a tip on installing those bushings.
The rubber bushings for the guide pins must be installed in the caliper and fully seated before the pins are installed and threaded into the adapter. Then, lubricate the bushings with water. Next, slip a positioner onto each guide pin, slide the pins through the bushings and shoes, and screw the pins into the adapter. If you try to put the bushings on the guide pins and then push them into the caliper, the bushings won't seat properly. If you should succeed in getting the pins started in the adapter, you'll only manage to ruin the bushings and the positioners.
Do these guide pins have to take all the braking loads?
No, Joe. As a matter of fact, the caliper is a precision sliding fit in the adapter. At 4 points, machine surfaces on both the caliper and the adapter maintain caliper alignment. These surfaces take all of the braking loads.
Before we go any farther, I think it's high time we explained how one big piston can do the work of 4 smaller ones. Several things enter into this, including the basic principle of equal and opposite action and reaction.
Come again, please?
Here's a familiar example of what that means, Joe. When you tighten the screw of a C-clamp against its seat, the screw pushes against the seat. That's action. But the seat pushes back against the screw an equal and opposite amount. That's equal and opposite reaction. If you find this hard to believe, try putting your hands out in front of yourself and leaning your weight against a wall. Now, imagine what would happen if someone suddenly took the wall away so that it wasn't pushing back against your hands.
I get the picture.
Good. So now you understand that 2 of these small pistons used in other brakes do the acting, and the other 2 actually provide the reacting force. In other words, our one big piston only has to do the work of 2 of the small pistons.
But that big one doesn't have as much area as 2 of the smaller ones. How come?
You're forgetting that braking depends on lining friction as well as piston force. The coefficient of friction of the lining used with the single piston brake is about 50% higher than the lining used with a 4-piston brake. This more than offsets the difference in piston area.
Okay, Tom. I'm convinced that 1 piston can do the work of 4, but I have another question. Why don't we use discs in the rear as well as in the front?
Disc brakes in the rear would complicate the parking brake design. Drum brakes provide a simple and effective mechanical parking brake system. To provide good parking brakes with discs would require very high apply force and a bulky and complicated leverage system.
Speaking of apply forces, much higher brake shoe force is used with disc brakes. Since the disc is actually clamped between the 2 shoes, the apply force is always equal on both sides, so there's no disc distortion, even at high temperatures. Less lining area is needed than with drum brakes to provide equal or greater braking. However, the disc brake lining material is quite special.
Tech's right, Joe. The lining material is much harder so it can withstand the high compression force needed to produce good braking. These harder linings can stand more heat and are more resistant to brake fade. In addition to being harder, disc brake lining is much thicker to provide good lining life. As the lining wears, the piston moves farther out of its bore, so disc brakes are inherently self-adjusting. Since the disc brake pistons are big and move outward quite a way to compensate for lining wear, more fluid capacity is needed in the reservoir of the master cylinder.
Before we get into the master cylinder and the rest of the hydraulic system, I'd be much obliged if someone would please turn the record.
I suppose this master cylinder is just like any other, but would you review how it works?
Sure thing, Joe. But I want to warn you, it isn't exactly like or interchangeable with any of our other master cylinders. All tandem master cylinders have two separate brake fluid reservoirs arranged one behind the other. However, a single cylinder bore is used, and the two separate pistons operate in tandem. It's a lot easier to keep things straight if we call the rearward piston the primary piston, because it is actuated directly by the brake pedal. Besides, the primary piston supplies pressure to the front brakes, where more of the braking is done. The piston at the forward end of the master cylinder is the secondary piston. In normal operation, hydraulic pressure from the primary piston operates the secondary piston. The secondary piston supplies pressure to the rear brakes. Here's how those pistons work. When the brakes are applied, the weaker secondary piston spring is compressed slightly by the stiffer primary piston spring. The secondary piston is pushed forward, and the secondary compensating port is closed off. Pressure starts to build up in the forward chamber. At the same time, the primary compensating port has also been closed off. The right amount of fluid is trapped in front of each piston, and pressure is developed in both the primary and the secondary chambers.
You still haven't told me what's different about the master cylinder for these brakes.
The master cylinder for the single piston disc brake has a longer stroke and greater capacity than most of our other master cylinders. What's more, the division of capacity between primary and secondary systems provides more fluid reserve for the front disc brakes. Now, here's the rub. The master cylinder for Coronet or Belvedere equipped with a Hemi engine and disc brakes looks exactly like the master cylinder used with single piston disc brakes. But they must not be interchanged. As a matter of fact, neither the pistons nor the assembly should be interchanged. So don't mix up the hardware.
Thanks, Tech. And while we're on the subject of master cylinders, here's a tip worth remembering. If you ever run into a case of brakes dragging because the master cylinder won't compensate, don't forget to check the stoplight switch. If it isn't properly adjusted, it will keep the pedal from returning far enough to open the compensating ports.
I'll remember that. Now, is there anything else different about the hydraulic system for these brakes?
There are a couple of differences, so let's review the rest of the system.
As you probably know, the residual valve for the rear brakes is located in the forward or secondary outlet of the master cylinder. No residual valve is used in the primary or disc brake outlet.
Why do we need a residual valve?
The residual valve maintains a light pressure in the rear brake cylinders. This keeps air from being sucked past wheel cylinder piston cups when the brakes are suddenly released. Residual pressure expands piston cups tight against the cylinder wall. A residual valve must not be installed in the primary outlet. Since disc brakes have large pistons and no shoe return springs, residual pressure in the primary lines would make the disc brake shoes drag and wear out prematurely. And now let's look at this warning light switch. The brake warning light serves a dual purpose. In addition to warning the driver if pressure is lost in either the primary or secondary hydraulic system, it warns him if the parking brake is on as soon as the engine is started. The primary brake line from the master cylinder is connected to one end of the switch, and the line for the front disc brakes is connected at the same end. With the single piston disc brakes, one outlet at this end of the switch is plugged, and you'll see why a bit later. The secondary master cylinder line is connected at the other end, as well as a line leading to the rear drum brakes. At this end of the switch, one outlet is plugged on all applications. Now, inside the switch, a barbell-shaped double-headed piston with an O-ring in each end separates the front brake hydraulic system from the rear brake system. Two small coil springs keep the piston centered as long as the pressure is the same in both systems.
If pressure is lost in one system, for example, the front brakes, pressure in the rear brake system pushes the piston off center. As soon as the piston moves far enough to touch the ground contact, the warning light comes on. The springs in the switch are quite stiff, so minor variations in pressure won't turn the light on. For example, residual pressure in the secondary system will not cause the light to come on even when primary system pressure is released. Although drum brakes have different characteristics than disc brakes, the single-piston disc brakes are designed to give excellent balance with the new rear drum brakes. However, on icy or slippery roads, it is desirable to reduce front-wheel braking. That's where the metering valve comes in. It cuts off pressure to the front brakes in the range from about 10 psi to about 115 psi.
Just how does that valve work?
With this brake setup, there's only one brake line from the warning light switch to the metering valve. That's why the other front brake outlet in the warning light switch is plugged. There are two lines leading from the metering valve, one to each front brake. Inside the metering valve, there is a check valve and a valve seat. The valve seat is mounted in a valve plate. A spring holds the valve plate closed. The check valve in the upper end of the push rod is normally opened to ensure complete release of the disc brakes. As soon as the brakes are applied, pressure pushes on the diaphragm at the lower end of the push rod. It only takes about 10 psi to move the diaphragm and push rod far enough to seat the check valve. Closing the check valve cuts off pressure to the front brakes. This provides good braking and steering control under slippery operating conditions because it reduces the likelihood of front-wheel skid. When master cylinder pressure gets up to about 115 psi, the push on the check valve and valve plate overcomes the valve spring and unseats the valve plate. From about 115 to 500 psi, the pressure difference between the primary and secondary is gradually reduced until pressure to front and rear brakes is the same.
What's the difference between a metering valve and a proportioning valve?
A proportioning valve reduces pressure to the rear brakes to delay rear wheel skid on hard braking. The metering valve holds off pressure to the front brakes under light braking conditions. It's sometimes called a hold-off valve. To quick check the metering valve, apply the brakes gently. A very slight bump will be felt at about 1 inch of pedal travel. This signals the opening of the valve plate, admitting flow to the front brakes. If you have a helper, watch the end of the metering valve push rod as the brakes are applied. The rod should move out of the valve slightly as the brakes are applied and move back into the valve as the brakes are released.
And here's something else to remember. The metering valve affects the procedure for pressure bleeding the front brakes. Since the pressure bleeder is usually operated at about 30 psi, the metering valve will close and the front brakes won't bleed. If you use a pressure bleed tank, hold the metering valve push rod up while bleeding. Do not force the push rod beyond its normal open position, and never use a block or a clamp to hold the valve open. Here's why. If you block the valve open and apply the brakes, the block will keep the diaphragm extended. As a result, full pressure will rupture the diaphragm. If that happens, the valve will be ruined and you'll lose the fluid for the front brakes.
I'll remember that. Now tell me, is this one of the rear brake drums used with the single piston discs?
Yes, Joe. It's one of the new finned and flared 11-inch drums.
You'll be glad to know that this year we have a new parking brake cable assembly. It has stiffer return springs and cable lubrication has been improved. This new cable ensures parking brake release and reduces the possibility of rear brake drag. It can be used on previous models, providing you always replace both rear cables. One last warning before we sign off. With these new disc brakes, never use a 15JK wheel. You must use either a 15JJ wheel or a 15K wheel. And now, I want to thank Tom for telling us about the new single-piston disc brake system, and thank Joe and you fellas out there for being such good listeners. Before any of you tackle one of these new brakes, get out your service manuals. And don't forget to use the extra information in this month's reference book.